Okay, let's start our unit on fluids. First of all, what's a fluid? Okay, so there's basically four states of matter if you include plasmas, but three main states of matter that we interact with: solids, liquids, and gases. Now, in a solid state, the atoms remain in contact with each other and they're sort of locked in position. They can't move. So a solid does not take the shape of its container and therefore it is not a fluid. A fluid is any state of matter, that being a liquid, gas, or I guess plasma, in which the substance can take the shape of its container. And that's because the molecules are not locked in position; they can slide past each other. So that means, for the most part, in this unit, we're going to consider a fluid to be either a liquid or gas state, and in most cases, we'll be talking about liquids. Now, we're going to constrain our discussions in this unit only to what's called an ideal fluid. So, an ideal fluid is a simplified representation of a fluid. Let's just try to make things easy, okay? So basically, we're going to say it has these properties. It is incompressible. That means you put under pressure, it doesn't change its volume. Now, this is definitely not true for gases. So there's certain situations, like with static fluids, that we can consider gases. But for the most part, this is going to force us to think in terms of liquids. Well, that's one thing. The other one is it has no viscosity. So viscosity is basically an internal force that makes it difficult for molecules to slide past each other. Uh, it dampens its ability to flow. So we're saying in an ideal fluid, that's not present. And also, there's no turbulence. And what that means is when the particles are moving, they're all moving parallel to each other. All moving parallel to each other. They're not moving at different angles relative to each other. Okay, now we're just going to have to shift for a moment and talk about density, because density is a big aspect of what we need to talk about when we're talking about fluids. Excuse me while I drink a cup of coffee. So basically, I think you remember this from chemistry. You probably remember this from middle school. Heck, you probably remember this from elementary school. Density is basically the amount of matter present in a given unit volume of a substance. So density is mathematically defined to be mass divided by volume. We use the rho symbol to represent density. So rho is equal to m over v. And in chemistry class, I would imagine you probably mostly measured in grams per milliliter. Mercury has a density of 13 grams per milliliter. Zinc has a density of 7.2 grams per milliliter. But we're using the MKS system. So we need to talk about newtons. We need to talk about meters per second. So we're going to use kilogram meters cubed instead of grams per milliliter. And that's a lot more matter. So there's a lot more mass. So it's as simple as this. The conversion is 1 gram per milliliter is equal to 1,000 kilograms per cubic meter. And it's not so hard to do. So this is what we'll use, although you may have gotten used to this in other classes. Now, density is basically a property. It's a physical property that a substance has, something you can use to identify it. We're not going to really concern ourselves with that too much in this course, but let's just point this out. So, for instance, water has a density of 1 gram per milliliter. It has a density of 1,000 kilograms per cubic meter. Wood, and there's lots of different kinds of woods, but let's say generic wood has a density of 0.6 grams per milliliter. Well, that'd be 600 kilograms per cubic meter. Steel is 7.8 grams per milliliter, 7,800. And air is a very small amount of 0.0012 grams per milliliter, which is 1.2 kilograms per cubic meter. Now, it's also worth noting that 1 milliliter is equal to a cubic centimeter, and that 1 gram per cubic centimeter is equal to. So when we say milliliters, we often are thinking in terms of cubic centimeters. All right, let's keep going here. Sorry if this one gets a little bit long. I don't mean for it to. I can't seem to get past my. Okay. You know what? You know how to calculate density. I'm not going to do this. You can look at the slide presentation of this, but I think we all know how to calculate. Well, okay, I won't. So if I said, what is the mass of a steel ball that has a density of 7.8 grams per milliliter and a radius of 5 centimeters? Report your answers in kilograms. Okay, so I start off with density equals mass over volume. So therefore, mass is equal to density times volume. Now, what's the volume of a sphere? Well, it's 4/3 pi r cubed. And yes, you're expected to know that, but it's also on your AP equation sheet. Now, therefore, what that means is mass is equal to density times 4/3 pi r cubed. So 7.8 times 4/3 pi it has a radius of 5, okay, so 5 cubed. So here's what I get for my mass. So I had to convert that into kilograms. So it's a little bit over 4 kilograms. All right, now, Density aside, let's talk about pressure. We're going to come back to that. Density is a big thing in this unit, but right now let's just talk about pressure. Pressure is really what makes this unit a little bit different. It's a little bit hard to wrap your head around, okay? So pressure is a measure of the amount of force exerted per unit area. All right. So for instance, look at this. Let's say I have a cube, and I tried to draw a cube. I am not an artist. This is a terrible cube. It's really it's sad. Okay. But anyway, this cube measures 1 meter by 1 meter by 1 meter, and it's made out of wood. So I have 600 kilograms of wood here. Right. So what is the pressure that this would exert on the floor? Well, the area is going to be 1 meter times 1 meter, or 1 square meter, and the force of gravity, the amount of force being applied, is going to equal to mg. So that's 6,000. So that's 600 times 10. So I end up with 6,000 newtons per square meter, or 6,000 newtons per square meter. Now, instead of writing this all the time, newtons per square meter, we're going to define this as a Pascal. Pascal was this guy who, in the 1700s or something like that, he did a lot of study into pressure. And so he named the unit of pressure after him. Now, 1 Pascal is defined to be 1 Newton per square meter. Easy enough to remember, right? The thing is, that's a really small amount of pressure. Like 1 Newton, that's not a lot of force. That's over 1 square meter of area. That's not a lot. So we often deal with kilopascals, which would obviously be 1,000 pascals. So 1 kilopascal is equal to 1,000 newtons per meter, or 1,000 pascals. Now, I should point out, even though it probably won't come up on the AP test, it may come up. I know a lot of you use like outside sources for prepping for the AP test, whatever. And when you do that, you might notice that there's a lot of units for pressure out there. It can be measured in atmospheres. We say at Earth's surface, you have 1 atmosphere of pressure. It can be measured in pounds per square inch, I'm sorry to say. Or it can be measured in bars, which is basically barometric pressure units, or millimeters of mercury. But we're just going to use pascals and kilopascals. All right, so consider this. Imagine if I have 1 kilogram of solid sitting in a jar. Okay, so this is my pathetic attempt to draw 2 cylindrical containers. All right, the top is circular, the bottom is not. Don't ask me why. Okay, so if I put 1 kilogram of solid in here, it will apply a force per unit area, but it will only apply that in the downward direction, directly underneath the solid. But remember, a liquid takes the shape of its container, and therefore the force that it's exerting will be exerted in all parts of this liquid. So it's not just on the bottom of the container, but all parts of this container are going to experience this force. That's the difference between fluids and solids, is that fluids exert pressure in all directions. Now, College Board does want you to have some understanding of the molecular nature of pressure. So here's my attempt to try to get that across to you. Okay, so imagine I have the side of a container here. I have a molecule traveling towards it. The molecule is going to hit the wall. The wall is going to apply a force to the molecule, and the molecule is going to apply the same amount of force to the cylinder, right? The wall is the container, because that's Newton's third law for you, right? So after the interaction, the molecule will be traveling away from the wall. And so this is the source of the force, the interaction between individual molecules and the walls of the container. Now, the idea is sometimes these molecules are not going to be moving completely perpendicular. Sometimes they're coming in at angles. So when they come in at an angle, they're going to come in like this. They're going to go out like this. The only aspect of this motion that is going to contribute to pressure is that component of it that is perpendicular. The component that is parallel to the component of motion that's parallel to the container wall, that's going to be undiminished. There's not going to be any change in momentum this way. There will be change in momentum this way. So it's only that perpendicular component that we're concerned with. Now, in reality, in a real container, you're going to have things going in all different directions. So it's sort of the sum of these gajillions of interactions. All right, that's what College Board wants you to know. But now I'm going to try something here. I just want to try to get you to visualize less than a gajillion. Okay, so imagine I have this nifty golf ball launcher. Okay, and it's going to launch 5 golf balls all at once towards this 1 square meter surface, handy unit to use, that's connected to a spring that has a spring constant of 60 newtons per meter. Well, when these golf balls make contact, individually, they each apply a small force as they ricochet off, but I'm going to sum that force over there. I have now 5 golf balls, and as they collide with it, they're going to cause the spring to be compressed. So let's just say it compresses 0.1 meter. Well, now what I'm going to say is, well, spring force is equal to negative K delta X. K I just said is 60, delta X is 0.1. So therefore that's 6 newtons of force that's being applied by the spring against the surface. That means there was 6 newtons of force being applied by the golf balls on this 1 square meter area. So 6 newtons over 1 square meter, that's 6 pascals worth of pressure. It's the exact same thing. You just have gajillions of particles, each with significantly smaller mass and moving in directions that are fairly random. But the sum of all the perpendicular forces, that's what gives us pressure. Okay, let's move on. All right. So at any given point in a static fluid, so a static fluid is one that's not moving, okay? It's just at rest. So at any point in a static fluid, the fluid pressure is going to be the same in all directions. So pick any particle, any part of the wall, the pressure is always going to be the same in all directions. Otherwise, this particle wouldn't be static, would it? If there was more force in one direction than the other, it would move, all right? So that's one of the central ideas of static fluids is that at a given point in the fluid, the pressure is the same in all directions. Now, one thing that's worth noting, and that's going to come quite a bit in this unit, is that if I was to move downward in a liquid, then what would happen is as I go downward, and you probably notice if you swim into a swimming pool, your ears start to hurt. And the reason is you're feeling the weight of all the water on top of you. All right, so it's the sum of all those molecules pushing down on you that's making the pressure. We call this hydrostatic pressure. So essentially, hydrostatic pressure increases with depth. And it's basically the pressure exerted on the fluid as a result of the gravitational force acting on all the molecular particles above you in that fluid. So the good news is the formula for hydrostatic pressure is pretty easy. It goes like this. Hydrostatic pressure, and by the way, I should just be straight up with you. They're not going to use this notation. I tend to use notation I think a little bit intuitive. College Board, not so much. So anyway, the hydrostatic pressure is equal to rho, the density of the fluid, times gravitational acceleration or gravitational field strength, times we use H, but what we really mean is how deep into the fluid you are. The deeper you go, if you double your depth, you're going to double the pressure because there's twice as many molecules stacked on top of you. So hydrostatic pressure equals density of fluid times G times depth. Now, this is kind of an interesting thing. Sorry, I'm going to keep drinking this coffee. I don't want to get cold. All right, so I have, and I stole these off the internet. Sorry about that. I have 5 just crazy different containers here, right? But the thing is, they all have the same depth. So the pressure at the bottom of each of these is going to be the same regardless of their crazy shapes. And the reason is hydrostatic pressure has nothing to do with anything other than the density of the fluid, the depth between the top of the fluid and the place where you're measuring pressure, and the gravitational field strength. It is worth noting, and I don't know if you've ever done this, but if you could say, if I put a container in an elevator and hit the up button, it's as though gravitational field strength got stronger, so the pressure would get bigger, okay? And conversely, if it went down the opposite. I don't know if they ever do that, but it is worth noting that G isn't always necessarily going to be 10. All right, and well, this is my attempt at making, that looks pretty good, don't you think? Okay. So let's just try this one. What would the hydrostatic pressure be at points P1, P2, and P3? Do not let the shape of this container have any influence on your answer. Basically, from here to here is distance h. From here to here is also distance h. All I have to say is, well, if I have a pressure sensor here, where the fluid is pushing up on it here, it's just going to be equal to rho gh, because rho is the density of the fluid, g is g, and this is at a depth of h. If I look at 2, now instead of the fluid pushing up is pushing to the right, but it's going to be pressing with rho 1.5 hg, okay, or 3 over 2 h. And then at the bottom, now here, the fluid's pushing, the pressure's pushing down on it, and it's going to be equal to rho g2h. Really straightforward, okay? All right, now let's try this here. Imagine if I took a 1 meter by 1 meter square area and made a column that went all the way. Imagine I have a container that's 1 meter by 1 meter in cross-sectional area. It's made of this magical substance that has no mass. And this container goes all the way up through the atmosphere to outer space. Now what I do is I start off, I seal the container, I pump all the air out of it. And now I let the air back in. And what I'd find is the mass of it would go up. And how much would the mass go up? Well, it'd go up by about 10,000 kilograms. In other words, for 1 square meter column, if you go all the way up to outer space, that container has 10,000 kilograms of air molecules in it. which would have a weight, therefore, of 100,000 newtons, and therefore a pressure, since it's a 1 square meter area, the pressure would be 100,000 newtons per square meter, or 100,000 pascals, or 100 kilopascals. Now, technically, I rounded the numbers a little bit. It's really more like 101.38 kilopascals, but we'll just round it to 100 to make our life easy. The point is, the atmosphere exerts a hydrostatic pressure. Now, the thing is, gas, the atmosphere is compressible, so you can't just do the rho GH, because the rho changes with height. The rho is greater down lower and is less up above. But we're not worried about that right now. We're just worried about the fact that the atmosphere does exert a pressure. Okay, and that pressure at sea level is roughly 100 kilopascals. Okay, so let's try this. The next thing we want to talk about is what's called gauge pressure, and this is a really important one, so please pay attention here. So let's just say I have a scuba diver, and she swims down 10 meters, and she looks at her pressure gauge. And if you scuba dive, if any of you've done that, you definitely have to use your gauges a lot, or you're going to end up dead. Okay, so she looks at her pressure gauge, and her pressure gauge says 100,000 kilopascals. All right, so we're going to call that the gauge pressure is 100,000. Now, as she ascends slowly, so she doesn't get the bends, she gets to a depth of 5 meters. She looks at it. Well, guess what? There's half as much water stacked on top of her. So there's half as much pressure. So instead of 100,000, it's 50,000. And when she comes all the way to the surface, now there's no water stacked on top of her. So her gauge pressure is going to say 0 kilopascals of water pressure. Right? So her gauge pressure went to 0. But it's worth noting that gauge pressure, that doesn't mean there's no pressure. There's still, many kilometers of air stacked on top of her. In truth, the pressure here is 100,000 kilopascals of air stacked on top of her. When she was down here, the pressure was really 200,000, but that's not what the gauge measures. So gauges, generally, a gauge pressure is going to ignore atmospheric pressure. It's basically, what is the pressure relative to the atmosphere? Because let's face it, when you and I walk around, we don't think about the pressure of the atmosphere. We ignore that. All right, so it's really important then to keep this in mind, because at the end of the unit, the most important idea we're going to deal with is called Bernoulli's principle, and you've got to understand gauge pressure. Gauge pressure does not have to be hydrostatic pressure. It could be, but it doesn't have to be. Consider a tire. I pump a bunch of air into this tire. As I do, the gauge pressure goes up and up and up. There's more pressure in it, the more molecules I put in here, right? PV equals nRT. Now, I have, say, 200 kilopascals of gauge pressure when the tire is fully inflated, about normal for a car. I hit a nail or something, get a hole in the tire goes flat. I look at the gauge pressure, it says 0. Well, that means it's really at atmospheric pressure. So let's talk about absolute pressure. So absolute pressure is the sum of the atmospheric pressure and the gauge pressure. We generally don't deal with absolute pressure. We generally only deal with gauge pressure, but we should note that absolute pressure is the total pressure acting on an object because of the various pressures. So basically, it's going to be the sum of the atmospheric plus the gauge pressure. Now, how do we go about measuring? Well, a common way of doing it is using an early way of doing it is using something called a barometer. And the way a barometer worked, I'm going to move myself over here. And I'm sorry if this is going a little bit long, but I'm not that sorry. Just pay attention, okay? So imagine I have a 1 meter long glass tube that's sealed off at one end and open at the other, and it is submerged in a container of mercury, of liquid mercury, okay, which has a pretty high density, 13 grams per milliliter, 13,000 kilograms per cubic meter. Now, what happens is, if I take this and I lift it upwards, what I'm going to find is that the atmospheric pressure here isn't sufficient to hold it all the way up in here, and it starts to move down. And what's inside here is nothing. There are no atoms in here. It is a vacuum, like outer space. So there is no atmospheric pressure here. Atmospheric pressure is 0 here, but it's not 0 out here. So let's think about this. Okay, so if I want to find the height of the mercury in the tube, here's what I got to say is, well, at this point here, I know that the absolute pressure is equal to atmospheric pressure plus hydrostatic, but hydrostatic is 0. So this pressure here is equal to atmospheric pressure. If I go to a point at the same depth over here, what I find is that there is no atmospheric pressure pushing on it, but there is a hydrostatic pressure acting on it. So therefore, what I can do is I can just say, what that tells me then is, since this is static, that atmospheric pressure that is equal to the hydrostatic pressure of this one here. Okay, so in other words, the atmosphere is pushing down hard enough to keep this column of column of mercury in place. So let me move myself. I don't know what just happened. I move myself out of there. So basically, what I would say is atmospheric pressure is 100,000 kilopascals. That the rho gh of this fluid must be equal to it, otherwise it would be moving. So I just put rho gh, and what I find is 0.074 meters, or 74 centimeters, or 740 milliliters and millimeters, and that's why we sometimes measure. The initial measurements of atmospheric pressure were in millimeters of mercury, because this is the only way people could figure out how to measure it. Okay. Now, these kind of problems you're going to encounter. So let's just see how we do these. And again, I apologize it's taking long, sort of. Okay. So if fluid A has a density of 1.2 grams per cubic centimeter, what is the density of fluid B? What? Well, here's what you got. We know that this is 100 centimeters. We know that this is 60, and we know that this is 80. And just your instinct should tell you, well, wait a second. So this one here must be heavier or more dense than this one here. That's why it's able to hold it up like that. All right. So the way we're going to solve this is we're going to say, well, at this point here, I know that the upward pressure is equal to downward pressure. So if I can figure out what the hydrostatic pressure of this one is here, it equals the hydrostatic pressure of this one here. So I'm just going to say that for this one here, I'm going to say rho gh here is equal to rho gh here. So I'm going to say G goes away. So rho A times HA is equal to rho B times HB. And therefore, if I want to solve for the density of B, I would just say, well, therefore, rho A is equal to HA over HB. And I can say, well, this one here is 100 minus 60, that's 40. And this one here is 100 minus 80, that's 20. And therefore, what I get is 2.4 grams per cubic centimeter. I didn't have to convert it to kilograms per cubic meter because it was unnecessary in this case, because I wasn't trying to find anything other than the density itself. This is a classic one. You'll definitely see this in the MCQ question, section of your test. Okay, so let P naught be the atmospheric pressure up here. Okay, an open cylinder has liquid of density rho to a height of h, and then it has a liquid of density 2 rho to a height of 2h. And I want to know, what is the absolute pressure at the bottom of the cylinder? Remember, absolute pressure, I have to take into account atmospheric pressure. Absolute pressure is equal to the atmospheric pressure plus the gauge pressure. The gauge pressure in this case is hydrostatic pressure. So I would say it's equal to P naught, that's the atmosphere, plus rho GH plus 2 rho G2H. So rho GH plus 2 rho 2G2H, that's equal to 5 rho GH. All right, I think that's the last one. Again, sorry. Okay, now, how would the absolute pressure at the bottom of container A compare to the absolute pressure at the bottom of container B? And the answer is, it's got to be the same. Don't let the shape of the container confuse you. I have the same depth of each of these. So since the depth is the same, the pressure is going to be the same. It only depends, the pressure, in this case, the hydrostatic pressure, only depends on rho, G, and H, not on the shape of the container. Okay, thanks for watching. I'll try to keep it shorter next time. Bye.